because we're doing a recording. We're discussing 8.1. It says part 1. I'm not sure why it says part 1. Maybe there's a second part. Is there other parts of this notes? Yeah, there is actually. There's a part 2. Okay. Anyway, so let's revisit linear motion, and this is called the definite integral as net change. So we're going to be looking at application of the integral, more specifically the definite integral. And what we're going to do is it's going to be really an application of the fundamental theorem of calculus. So this is how my way of kind of spiraling or reinforcing this essential concept for this course. Because what we're going to be doing is we're going to do an integral of a derivative. We're going to be doing the integral of velocity as a function of time times dt. And we're going to find that if you have a and b here, it's going to equal your antiderivative. Well, what's the antiderivative of velocity? It's going to be position. So this is what we're going to be doing a lot in these notes here. We're going to be taking the antiderivative of velocity. Let me actually type that up as a text box. Antiderivative of velocity for some interval a to b will represent the change in position from a to b. There we go. That's really what this section is really about. The antiderivative of velocity for some interval, which is this definite integral, obviously that's antiderivative, will represent the change in position. And we use s for position, by the way. Likewise, if you were to do the antiderivative or the definite integral, it's meant to go to green, from a to b of your acceleration function times dt, that's going to get you the velocity of b minus the velocity of a. So if I put that in a text box, antiderivative of acceleration for some interval a comma b will represent the change in velocity from a to b. Let me finish typing that. So that's also another thing we're going to see as well. And why? Because remember, what we talked about from the, from last week. We take the integral of from, a to x or a to b of f of x dx. That equal that, where capital F of x is an antiderivative of little f of x. That's what we're noticing here. And also the fact that when you take the antiderivative of, because, velocity equals s prime, right? So if I do that, then this essentially becomes this right here, where, okay, I'm doing the antiderivative of a derivative, it gets me back to s. So that's really what's going on here, this stuff. Well, let's go through these examples here right now. So you have a velocity, 2t minus 2 from 0 to 4. Find the position of the function at t equals 4 if s sub 0 equals 5. So there's two ways we could do this. We'll talk about the old way, which is using more geometry, I suppose. So you could do, actually, hold on. Let me make sure I'm not doing things out of order. Give me one sec. Okay, so remember, we know that velocity is ds or dt, or s prime. So s prime equals 2t minus 2. And we know that then s of t or s will equal t squared minus 2t plus c. So that's going to be the position function, right? That's just the antiderivative velocity. So this right here, and we actually, I think we kind of talked about this a couple weeks ago. That's antiderivative of velocity. T squared minus 2t plus c. Now what I could do, if I do s of 4, well, let me do s of 0 first. Because s of 0 equals 5, 5 equals 0 squared minus 2 times 0 plus c. So c is 5. So your function, and I'll just use a function notation. I wasn't using that earlier. S of t equals t squared minus 2t plus 5. Now if I want to find s of 4, 16 minus 8 plus 5 means you get 13. And no units here, so don't worry about the units. But that's how we would, I guess we'd call it the old way. I don't know. I mean, this all seems new to us. But that's something that we should be pretty comfortable with, right? That, you know, we know that the antiderivative velocity is position. So if there's velocity 2t minus 2, then the antiderivative of that would be t squared minus 2t plus c. If you have an initial condition, you know, 0, you know, when t is 0, s is 5. So plug in 5 for s, 0 for t, c is 5. Now you have your equation, t squared minus 2t plus 5, and then plug in 4 and you get 13. Great. So we're good there. We could also kind of write it like this too, in a more streamlined, efficient manner. I guess it's called a new way. As what I what I discussed at the beginning of these notes is that the integral from a to b of v of t dt equals s of v minus s of a, where we call this displacement or change in position, or delta s. You could think of it like that too. The advantage of this method is that you can use your calculator if the integral, or some other techniques, like you know, if you want to major in engineering, like you'll have to use some more sophisticated mathematical programs like Mathematica or something like that. They do integrals for you. So you can use your calculator or some program if the integral can't be done by hand. So that's why this is advantageous, doing this in this fashion here for part B. You can use your calculator if the integral can't be done by hand. So for example, we could say the integral from 0 to 4, because is that where we're going from 0 to 4, is that right? Yeah, 0 to 4, of your velocity function, which was 2t minus 2, must equal, and dt, by the way, sorry about that, must equal s of 4 minus s of 0. S of 4 is what we want to find. S of 0 we know is going to be 5. And then this right here, you can use your calculator if you want. Got my calculator right here. So hit alpha window, option 4, 0 to 4. I'll do 2x minus 2 dt. So I'm just plugging in my I'm doing dx, obviously. And I get 8. So see how that's much cleaner doing it that way, as opposed to actually doing the antiderivative by hand and kind of like find the antiderivative, then plugging in like, find the initial condition and then getting the equation, then plugging in 4. It's more streamlined this way. Let's try it again for example 2. Example 2, you're given a different velocity function. You're given a different interval. You want to find the position at t equals 8. Sorry, you're told the position at t equals 8 is 3.2. What is the initial position? So when I want the initial position, I want s is 0, or s at t equals 0. Okay, question in the chat. Under new way. Yeah, actually, I didn't fill this out. The FTC Part 2 states that f is antiderivative. Yeah, we've that capital F of B minus capital F of A equals the integral from A to B of little f x dx. Sorry about that. That's what's supposed to be there. That's what we're doing. We're doing FTC Part 2. This is kind of an application of all this stuff. Okay, now let's look at example 2. For example 2, okay, great. You got that funky velocity function. So you're going from 0 to 8. Of that really crazy function, -2 times e cosine t dt. And that's actually impossible to do by hand, just so you know. Equals, and I'll tell you to use your calculator on an exam, equals s of 8 minus s of 0. Remember f of b, capital F of b minus capital F of a, where s is the antiderivative. Remember, s, which is position, is the antiderivative of velocity. Remember, this is now an extension of the fundamental theorem of calculus, or an application of it, where if velocity is a derivative, and remember, velocity is the derivative of position, right? So fine, great. You're doing the definite integral of a derivative gets you back to your original, which is position in this case. Anyway, s of 8 we know is 3.2. S of 0 I do not know. That's what we're trying to find. And we're going to use a calculator to work this out. So I want to make sure you guys are doing it correctly in the calculator. So the left side here, go and punch in your calculator and go and type in the chat what you get. I want to make sure you guys are doing this correctly. And by the way, make sure you're in radian mode. Very important. Make sure you are in radian mode. So -2 times e cosine x my calculator's a little slow here. Good, I get 2 people getting the same thing. I get -22.39. Yes, very good. It should be -22.39. Subtract that by 3.2, which is -25.59. By the way, we should actually round to 3 decimal places. So we should put 0.590, but it's negative s of 0 equals that. So then s of 0 is 25.590. That's my initial position. And so with this velocity function, after 8 seconds, now my position is 3.2. Great, that's what happened. Okay, so let's keep moving here. Let's look at another one. This one was a doozy. Okay. Let's see here. Let's draw a diagram first. So we got 2t minus 2, same velocity function as before. Okay. So y-intercept of -2, x-intercept is going to be 1. You have that as a point. You have that as a point. You have that as a point. Great. Okay. Find the total distance traveled if t equals 4, if s is 0 equals 5. Okay, this is kind of interesting. Now you ask me to find the total distance. Not necessarily change of position. Remember, change of position is displacement. Remember we talked about, like, if I were to get up and walk around, like if I were to get up and walk to the end of this room and back, my displacement would be 0. But when I walk back and forth, my total distance is not 0 because I've actually burned some calories walking back and forth. Or if I had like no one really has a Fitbit anymore, but if you, or you know, a lot of people like the Apple Watches or some sort of wearable that tracks your steps, it will still show that I've taken steps, even when I get back to the same place. So total distance is a totally different thing than displacement. Displacement is change of position. Total distance means how much you actually traveled. Now remember, direction is given by the sign of velocity. So it's pretty clear my velocity is negative from 0 to 1. In fact, if I do a sign chart for my velocity, here's at 0, here's at 1, here's at 4. My velocity is clearly negative here and positive here. And obviously, my velocity is 0 at t equals 1. I'm at rest at t equals 1. And we see that from the graph as well, or you can see from the equation. So you have to be mindful about that. The particle changed direction at t equals 1, obviously. So the particle was going in opposite direction from 0 to 1, then all of a sudden it stopped at t equals 1, then it went in the positive direction from 1 to 4. So the displacement from 0 to 1, if you integrate that from 0 to 1 of my velocity function, which is 2t minus 2 dt, if I were to work that out, it's traveling in a negative direction. And if you were to work that out, that actually would equal -1. In fact, you could even do geometry here, right? That's 1, that's 2, but it's below the x-axis, so it's -1. What about my integral from 1 to 4? Let me do a different color for that one. We'll do blue. So from 1 to 4, what's my integral here now? Well, now I'm going the positive direction. And by the way, I could just use some geometry if I want. Or you can do the antiderivative 2t minus 2 or use your calculator. I don't really care. That's 3 and that's 6. That's going to be 9. So your displacement would be 8. But the total distance traveled is actually going to be 10. Total distance is actually going to be total area. Displacement or change of position is actually net area. Remember we had that discussion last week about net area and total area. I think that was in 7.1 if I'm not mistaken. No, 7.2. Maybe. Nope, it was 6.4 actually. All right, third time's a charm. Yeah, net area and total area. So remember total area is when we took the absolute value of our function we're integrating, and then we integrated, or any area that was below the x-axis, we flipped it over the x-axis to treat as positive area, and that was total area. And that's what's happening here. Distance travel is actually going to be like total area. So a way you can actually do this in the calculator is do the absolute value of velocity instead. So the absolute value of velocity, by the way, in case you forgot from last semester, is speed. Because speed does not involve direction. So the absolute value of velocity is speed. So if you took the integral of speed, so you gotta be very mindful about this stuff because people can get this stuff really confused here. If you graph the absolute velocity, remember we were like right here, so I got to flip that over. So now it's going to look like this, and then they had dots here, here, and here. Remember, this is speed. And total distance travel will equal actually the integral from your t1 to t2, if those are your two different times, of the absolute value of velocity as a function of time times dt. So you can just do that instead. So displacement is this. That's what we did in the previous page. Displacement and distance are not necessarily the same, especially if you're going the opposite direction. So this could equal distance only if your velocity is always positive, if you're staying in the positive direction. That's not true for 2t minus 2, that function that we just dealt with in this example from 0 to 4. Total distance travel equals displacement traveling in the positive direction plus absolute value of displacement traveling in the negative direction. So you got to look at both negative and positive direction, and the negative direction now becomes a positive value. Or you can just use your calculator. And remember, you got to do the absolute value of velocity, not the absolute value of the whole thing. That's the whole thing, just gives you this right here is actually just the absolute value of displacement. Who cares about that? You know, in fact, actually, we want displacement to be sometimes negative, so we don't want that does nothing for us. The absolute value of the whole integral. We got to do the absolute value of the velocity and then integrate it, and that's where you use a calculator to help you out. Okay, so actually that wasn't too bad. I thought this was going to be really lengthy. So let's move on to the next page, and then I think that's a good place to take a break. Okay, let's do example 4. You have another velocity function. Now this time it's 3 times cosine 3t. Intervals from 0 to pi over 2. Determine the particles move to the right, to the left, and stop. Fine. Find the particle's displacement. Fine. What is the final position of the particle, which is at pi over 2, when you have initial position of s of 0 equals 5? Find total distance traveled. Okay, so we're going to knock all these out pretty quickly. And then after that, yeah, okay. So let's do ABC first, because that's going to be pretty quick. So let's just look at the graph, make sure we understand the graph correctly. This is at t equals 0. By the way, it's also good to identify these points. I believe this is going to be at 2 pi over 3. Remember, period is 2 pi over b. Remember from pre-calculus last year. And b is 3 here for our function. Remember, that's b. So that's my period. So half the period is pi over 3. And this is going to be at pi over 6. And that right there is going to be at 3 pi over 6 or pi over 2. Because pi over 2 is 3 pi over 6. So pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. Or pi over 6, pi over 3, pi over 2, and 2 pi over 3 if you simplify those fractions. So velocity equals 0 at 2 places. Pi over 6 and pi over 2. It's moving to the right. And we're going to do this as intervals. Let me actually do as a text box, so it's a little easier for you guys to kind of see what I'm doing. Give me a sec, I'm just typing this up here. Actually, we're only going up to pi over 2, so sorry, I'm kind of tripping here. We're only going up to pi over 2. So I actually only care about this part of the curve. Remember, that's our interval, right? So I don't care about this stuff here. But still good to know it's 2 pi over 3. But I don't care about that anymore. So I'm going to reference 0 to pi over 6 because my velocity is positive. I'm going to the left when my velocity is negative. In that case, if I do as a text box, that's going to be from pi over 6 to pi over 3. And the velocity is 0 at pi over 6 and pi over 3. So, sorry, pi over 2. So you do it at open intervals there. But the velocity was positive at 0, so that's why we put 0 there. And you're stopped, obviously, at pi over 6 and pi over 2. That's where we're stopped. Pi over 6 and pi over 2. Okay, so displacement now. So I already took care of part A. That's done. For part B, the displacement is just simply the integral from 0 to pi over 2 of my velocity function. If you want to do it by hand, feel free to do so. The antiderivative cosine sine, it's just going to be sine 3t, and you're valuing that from 0 to pi over 2. What happened to all the 3's here? Well, the thing is that if y equals sine 3t, you could do a u sub if you want, but just to save time, if you do derive that, I know it's going to be 3 cosine 3t. So I know I've done this correctly. What you're doing is that it's kind of the reverse of the chain rule. You see a 3 right there. So it's almost like, yeah, fine, you have this 3 here, but you're dividing by 3 anyway. So you would actually divide by that 3 when you integrate this, when you have a linear coefficient. And then it crosses off the 3 that's being multiplied to cosine. So it's almost like they cancel out anyway. So you have sine of 3 times pi over 2, which I know is negative 1, minus sine of 3 times 0, which I know is 0. So the answer is just negative 1. That's my displacement. So that's your displacement. So obviously, and it kind of makes sense because if you think about it, that's all positive area right here. And that's negative, and that negative area is more than that positive area. So overall, it should be a negative, negative displacement. Part C is asking for the final position. That's just using what we did on page 1. So remember, the integral of our velocity, right, from A to B of our velocity function equals S of B minus S of A, right? We already worked out the velocity in part B. That was negative 1. And in this case, we're going from, we want S of pi over 2, right? So that's going to equal S of pi over 2 minus S of 0. Well, S of 0, you're told it's 5. So negative 1 equals S of pi over 2 minus 5. So S of pi over 2 equals 4. So that's part C. Okay, any questions about A, B, or C here? Again, you're moving to the right when your velocity is positive, moving to the left when your velocity is negative. You're stopped when your velocity is 0. That was part A. The graph helped us with that. Displacement is simply the integral of your velocity from whatever interval you're looking at, which we talked about on page 1. So that's what I did. I got negative 1. And then if you want to find the change of position, or sorry, displacement is a change of position, but if you want to find a particular position at a particular time, then you set your displacement equal to that change in position. So like we know the integral from 0 to pi over 2 of my velocity is going to be S of pi over 2 minus S of 0. I know S of 0 is 5. So negative 1 equals S of pi over 2 minus 5. S of pi over 2 is 4. And I don't think we need to put units because we're not giving units here at all. No, displacement is not total area. Displacement is net area. Displacement's not, no, total distance is total area. Displacement is net area. My net area here is -1. Let's actually work out part D, so that will make a little more sense. Yes, we'll take a break after this problem. Don't worry. Yeah, we're taking a break after this problem. Actually, you know what? Let's take a break right now because I'm looking at part D. I'm like, let's take a break. It's 10:15. I did say we're gonna do a break. We'll come back. We'll actually do more of this, and I do want to. And then I think after that, then we'll do. Well, I don't know. The more I think about it, no, we'll do worksheets after the break also. So we'll finish off this problem, and then we'll yeah. So let's take a break and we'll finish off this problem. Okay, so let's do a break right now. So stop sharing.